Today on McColley Math, we're talking the fundamental theorem of calculus. Intro. Okay, good day. I'm Professor McColley. This is Math 200 Calculus 1, Lesson 24 on the fundamental theorem of calculus. Our goals for today. We're going to evaluate the definite integral using the fundamental theorem of calculus. We're going to understand the mean value theorem of calculus. We're going to find the average value of a function over a closed interval. We're going to understand the second fundamental theorem of calculus, and we're going to understand the net change theorem. In the last lesson, the definite integral was described as the area under a curve. These definite integrals were evaluated using limits and by making approximations using geometric shapes. In this lesson, the definite integral is evaluated using algebra and the fundamental theorem of calculus. First, the fundamental theorem of calculus. I know it's kind of funny that we don't get to the fundamental theorem of calculus until the last unit in the course, but there you go. Anyway, the fundamental theorem of calculus is if a function lowercase f is continuous over the closed interval a to b and uppercase f is an antiderivative of lowercase f on the closed interval from a to b, then this is the value of the definite integral. And so all you do is you integrate this function and then you plug in the upper limit of integration and the lower limit of integration, and then you subtract them. So some key concepts. First, the definite integral finds the area under the curve under the closed interval, and we can visualize the definite integral as an accumulator. It's summing up these values. The definite integral versus the area under the curve. Remember, the definite integral calculates the area between the curve and the x-axis. So if it goes below the x-axis, the definite integral counts that as minus area. And so if they ask you to find the area between the curve, you may have to break it up into parts. Please note that the graphing calculator will find the value of definite integrals, but it will not find indefinite integrals. It will also not take into consideration area under the x-axis. Remember, it will count that as negative. Therefore, you are responsible for learning the integration rules. And when you're allowed to use the calculator, you must check for places where the curve crosses the x-axis, just to make sure, especially if they ask you for the area under the curve. The mean value theorem for integrals. If f is continuous over a closed interval a to b, then there is a number c in the closed interval from a to b such that that definite integral is equal to f of c times b minus a. Now, this formula looks fairly simple, but what does it actually mean? Let's look at a quick demonstration here to try and make sense of this. Suppose we have a function f given by this yellow curve over a closed interval from a to b. The value of the definite integral of f over a to b is represented by the area under the curve shown here in purple. The mean value theorem for integrals says that there exists some value c somewhere between a and b, such that the area of the rectangle formed by the value of the function at c, shown here in light blue, is equal to the area under the curve over the same region. Since these two regions are equal, the value of the definite integral must be equal to the length times the width of the blue rectangle. The length is the height of the function at c, and the width is the length between a and b. Let's take a quick example. Find the value of c guaranteed by the mean value theorem for integrals over the given interval. All right, so if I wanted to kind of plug this in, I am going to get a function that's going to look, if I go from 1 to 3, it's going to be fairly steep and it's going to come down and get flat fairly quickly. All right, so I need to find a value c in between this. So what are we going to do? Well, first thing I'm going to do is I'm going to integrate this thing, and I'm going to use the definite integral. And so we'll be using the fundamental theorem of calculus here for the first time. So I'm going to integrate from 1 to 3 of 9 over x to the third dx. So here I'm going to rewrite so that I can do that integration. So we're going to do our integral from 1 to 3. But because 9 is a constant, I'm going to move that 9 out front. And then I'm going to move this x to the third to the top by making that exponent negative. And here I'm going to use the simple and so I'll have 9 and it'll be x to the negative 2 over negative 2. And we're going to evaluate for that from 1 to 3. And so using the fundamental theorem of calculus, we'll have 9 times, I'm going to plug in this 3, so I'll have 1 over negative 2 times 3 squared minus 1 over negative 2 times 1 squared. And if I make that calculation, I get 4. Now, what does that 4 represent? That 4 represents this area right here. The mean value theorem says that there has to be some value c here that when I calculate this f of c and I make the rectangle here, that area also has to be 4. So we got to find that. Shouldn't be too hard. We recall the mean value theorem says that the integral from a to b of f of x dx is equal to some f of c times b minus a. All right, we're going to plug in what we know. And we already figured out the value of the integral. It was 4. We need f of c. Now the f function was defined all the way back up here as 9 over x to the third. So we're going to make it 9 over c to the third. Now b and a were 3 and 1 respectively. So here we're going to simplify. And we'll have 4 equals 9 over c to the third times 2. And then we'll divide. So we'll have 2 equals 9 over c to the third. And here we'll use a property of proportions to switch c to the third and 2. That'll give me c to the third equals 9 over 2. So c is going to equal the third root of 9 over 2. And that is the value for c. Now, I'm not exactly sure what that's going to be, but it's clearly going to be more than 1. Box around that. Move on. Okay. Second fundamental theorem of calculus. If f is continuous on an open interval I containing a, then for every x in the interval, the derivative of the integral is equal to just f replaced with x. Now, I'm going to do an example for this, but essentially the shortcut is, in general, if everything fits the form here correctly, then essentially you can just take this x and plug it into the function and be done and not have to do a whole lot of work. Now, you're not always going to see it like that, but in the rare instance where you get all of the values to fit in the form very neatly like this, you can do that. The net change theorem reinforces the concept of the definite integral as an accumulator. And it says the definite integral of a rate of change of a quantity gives the total change or the net change in that quantity of the interval over a to b. As a quick example, if you have a rate of change, which we might say as a velocity, over a given interval of time, then the net change theorem, if you know what that velocity function is, then if you do the integral of that, you can find the net change in distance over that interval of time. Here we have an example where it says find f prime of x, and it is given f of x is equal to the definite integral from 1 to x of the fourth root of t dt. Now, this thing fits this second fundamental theorem of calculus. We have a constant, we have a function, we have x as our upper limit of integration, and we have our variable of integration matching the function value. And so what we could do is everything fits. So if we wanted to take the easy way, we can just go and say that f prime of this thing is equal to the fourth root of x, and we would be done. All right, but this is not going to really be a proof, but if we use the fundamental theorem of calculus, then f prime of x would be equal to the derivative with respect to x of the integral from 1 to x of the fourth root of t dt. All right, so what does that mean? Well, d over dx, we're going to leave that alone for a moment. And I'm going to integrate, I'm going to rewrite. So we'll have t to the 1/4 power, so that I can use the simple power rule on it. So here we are going to rewrite. Here we want to use the simple power rule. And so we'll go d over dx of, this will be t to the 1/4 plus 1 over 1/4 plus 1. I suppose we could have done that in our head. Goes from 1 to x. And then we still haven't taken our derivative yet, so we got to write that. So this will be 4 over 5 x to the 5/4 minus 4 over 5 times 1 to the 5/4. Now, we could simplify that if we wanted to, but we're going to take the derivative of that. And so (5/4) times 4/5 is going to be 1. Reduce 5/4 by 1, we'll get x to the 1/4. The derivative of a constant is 0. So we get the fourth root of x, which is what we came up with way up there. Another example, a creek in your backyard is flooding and eroding the banks. The rate at which water is flowing past your house is 2 plus 0.01 t 1,000 gallons per hour, with t being the number of hours since you began observing the erosion. How many gallons of flood water travel by your home in the first 10 hours as you observe the flood? So this is an instant of the net change theorem. We're trying to figure out the total net change of a function that is itself changing. So essentially what we're doing is we are going to say that the net change in water is going to be the integral from 0 to 10 of this 2 plus 0.1 t with respect to time. Okay, so the integration is going to actually be fairly simple. The integral of a constant is just going to be 2t, and then the integral of this t to the first, we'll use the simple power rule on that, and we'll go 0.1 times t to the 2 over 2, and that will be evaluated from 0 to 10. So that's not too bad. I'm going to have 2 times 10 plus, and so 0.01 divided by 2 is going to be 0.05, and then it'll be 10 times 10 squared. And then from that we'll subtract, well, 20 plus, this thing turns out to be 5 minus 0 equals 25. And remember, this is in thousands of gallons, so our units will be thousands gallons. 25,000 gallons. All right. Moving along, the average value theorem for integrals. If f is a continuous function over the closed interval a to b, then the average value over the closed interval a to b can be found by 1 over a minus b times the integral from a to b of f of x dx. To think of this in simple terms, let's look at a quick demonstration. Let's suppose that we have 8 test scores shown here in blue. We know that the average of these scores is equal to the sum of the values over the number of values. In this case, we would add up the 8 test scores and divide by 8. But look what happens if we order these numbers and plot them relative to each other. They start to look like a function. Now these values are discrete and the average is easy to compute. But what happens if there is a continuous function over an interval? If we want to find the average value of that function over the interval, we can use the concept of the integral as an accumulator to quote-unquote add up the infinite number of points along the curve. So in our average formula, the sum of the values becomes the definite integral. The number of values becomes the length of the interval, and this is then rewritten to look like this. Example. The revenue of Professor McColley's wild widgets from the years 2005 to 2020 can be modeled by the function r of t is equal to 0.032t squared plus 0.5t plus 15, where r is the revenue in hundreds of thousands of dollars and t is the number of years since 2005. Find the average revenue for Professor McColley's wild widgets for the years 2005 to 2020. Now, first thing we want to know is number of years since 2005. That tells us that t equal to 0 is represented by 2005, and then the t equal to 15 will be representative of the year 2020. So the average value function is going to be 1 over b minus a times the integral from a to b of f of x dx. And so in this particular instance, our interval is going to be 15 to 0, or 0 to 15, I suppose. And our function will be this 0.032t squared plus 0.5t plus 15 dt. Now, I'm going to do this integral, and I'm going to do it fairly quickly, and we're just going to use the simple power rule on all of these. And so 15 minus 0 is just going to be 15. And so we'll have 0.032 times t to the third all over 3 plus 0, and I didn't do a very good job there. Make sure that we have that as a 0. 0.5 times t squared all over 2 plus 15t, and that is going to be evaluated from 0 to 15. Now, when I evaluate this, the good news is when I plug 0 into all of these terms, I'm going to get 0. So I'll have 1 over 15 times, let's simplify this, and I have it written over to the side. 0.32 divided by 3 is 0.0107, and that will be times 15 to the third plus, this becomes 0.25, and that'll be 15 squared plus 15 times 15, and we'll subtract from that. Now, if I plug 0 into these 3 t's, I'll get 0 for the whole thing. And when I add that up, I get 21.1575. And remember, this is in hundreds of thousands of dollars. So the average yearly revenue is, I put it in dollars, so this is hundreds of thousands, so if I move it there, that'll be millions. $2.15750. So $2,115,750 is my average yearly revenue over those 15 years. Well, that's all I got for today, folks. So, the Star Wars fun fact of the day. What was the name of George Lucas' first draft of Star Wars in 1974? So his first draft, he named it The Adventures of Luke Starkiller, as taken from the Journal of the Wills, Saga 1, The Star Wars, which is kind of a mouthful. I'm glad he just shortened it to Star Wars. That's a little bit easier to take. Well, that's all I got for today, folks. Have a good day.